Hi guys, in today's video we have a proof by induction. So this is our proposition. We can write it down as P of n. The first thing we need to check that this proposition holds for the base case, which is 1 in this case. So we need to check that P of 1 is true. So P of 1, we're going to substitute 1 into this. So every time that we have n, we're going to substitute 1, right? So P of 1 is summation from 1 to 1 of k squared is equal to 1/6 times 1 times 1 plus 1 times 2 times 1 plus 1. Notice that here we have 1 from 1 to 1. We're just going to substitute 1 into this k. So this implies that 1 squared is equal to 1/6, 2 times 2 times, this is 3. So this implies that 1, because 1 squared is equal to 1, and this is gonna cancel out. So 1 is equal to 1, therefore is true, right? So our P of 1 is true. Now we need to check whether P of n true implies that P of n plus 1 is true. We need to prove that P of n plus 1 is true, assuming that P of n is true, right? Our P of n plus 1 is going to be equal to basically substituting n plus 1 into this P of n. So every time that we have n, we're going to substitute by n plus 1. So our P of n plus 1 is summation k from 1 to n plus 1 k squared. Here we have 1/6 n plus 1. Here we had n plus 1. So it's going to be equal to n plus 1 plus 1, which is n plus 2. And here we have 2 times n plus 1 plus 1. Now this implies that this summation k squared is equal to 1/6 n plus 1 n plus 2. Here we have 2n plus 2 plus 1, which is basically plus 3. So we need to prove that this P of n plus 1 is true. So we're gonna start by the left hand side, and our goal is to get the right hand side. If we manage to get the right hand side, then our proof is done. So this is our goal. So we're gonna start with the left hand side. We can copy and paste it here. So this is our left hand side. We're gonna split the sum, start from 1 to n, and then we add the sum from the successor of n till this one here, the last one. So the successor of n is n plus 1, and the last term here is n plus 1, right? So this is basically equal to this. We just split the summation. Now if we go back to our P of n, we assume that P of n is true, right? And P of n is basically equal to this. You can notice that this is equal to the left hand side of this equality, so we can just substitute this into here, right? So let's copy this, and we're gonna substitute it here. So this is equal to, we paste it here, this plus this summation, and here we start from n plus 1 to n plus 1, so we can basically substitute this into our k. So this is equal to n plus 1 square. Now this is equal to, we're gonna put them on the same denominator, so we have n times n plus 1 times 2n plus 1, then plus 6n plus 1 square. Now this is equal to, we have a factor n plus 1 here and n plus 1 here, so if we factorize, have n plus 1 times, here we're gonna be left with n and 2n plus 1, so n times 2n plus 1, and here we're gonna be left with 6 times n plus 1, right? So 6 times n plus 1. Over 6. Now we can multiply here and remove the brackets, so this is gonna be equal to n plus 1 times 2n squared plus n plus 6n plus 6. This is equal to n plus 1 times 2n squared plus 7n plus 6 all over 6. Now we can factorize this 2n squared plus 7n plus 6. So 2n squared plus 7n plus 6, we can write it down as 7n. We can split this into 4n plus 3n, then plus 6. Here we have a factor 2n and a factor 2n, so we can factor 2n out, and we have n plus, here we're going to be left with 2. Then here we have a factor 3, so 3 out, and we're going to be left with n plus 2. Notice that we have n plus 2 and n plus 2. So if we factorize it, we have n plus 2, and we're going to be left with 2n and 3. So times 2n plus 3. So basically this is equal to this. Now we can write this by substituting this, right? So we were left here, so this is gonna be equal to n plus 1. We're gonna substitute this, so let's copy, times this all over 6, and this is our goal. As you can see here, this is our goal. So we can conclude that P of n plus 1 is true. So since P of n true implies that P of n plus 1 is true, we can conclude that P of n is true for every n natural number.